All right, it's 6:05. Let me pull up the building unit circle. Okay, the fill-in unit circle. Start getting comfortable with it. Practice filling it in. I'm going to give you blank copies so you can practice filling it in, or I'll put a link in Google Classroom to an online widget that you can type it in and it'll tell you if it's right or wrong. Yesterday we got through showing you how to fill in the coordinate points, that they come from the special right triangles. And then this over here in the corner, that's cool. Alright, so this over here in the corner is the part that you need to commit to memory. Since we're dealing with the unit circle where the radius is 1, if we are evaluating the sine of something, now we just have to get the y coordinate. If we're evaluating the cosine of something, we just need the x coordinate. And if we're evaluating the tangent of something, we need to divide y by x and then remember to rationalize. So that's what we practiced here. We jumped around. We went to the easiest ones first, where you're simply, actually I think it was these two. Those two are on the unit circle. You're just identifying the coordinate. Then we went to ones that are not on the unit circle, and you have to either add or subtract a rotation to get it on the unit circle, then find it, then write the coordinate. Then we did one that was quadrantal, which means you're using the numbers 0, 1, or -1. And then we did a tangent of one that's on the unit circle to show that you have to divide. And when you divide fractions, that's keep, change, flip. And then you just have to remember to rationalize. I hope you started the homework last night, because you could have knocked a couple out because it's this. Then this slide, as y'all were packing up, I was saying that this slide is just a matter of, can you type it in the calculator? How do you know that you need to be typing it in the calculator? It's by the directions. When it says round the answer to 4 decimal places, that means you're letting the calculator do the work. You're not using the unit circle. There is one requirement, and that is, notice none of these have a degree symbol. Y'all notice that? Because there's no degree symbol, so I'm going to make a note. Notice there's no degree symbol. Because there's no degree symbol, that means these are all in radian, which means your calculator needs to be in radian or you're going to get the wrong answer. Okay? Yes?
Yeah, current Grace is 6.5.
Thank you. So because these are radian measures, not degree measures, you do need to make sure that your calculator is in radian mode and you are literally typing it in. It's just, hey, do you know how to type this in? You don't have to find coterminal angles. You don't have to find reference angles. It's one of those where you should get this right. Can we get me one? Are you kidding? That's what I thought. That's really nice.
Thanks, Princess.
Let's see.
Andy, did you say something? Did you ask a question? Sorry.
Okay. So have you tried all 4? Or have you tried the first 3? You're going to 4 decimal places. You try them before you look up here. And then look up here and see. If you got the same thing. When you get to D, you've got to go back to like 6.1 or 6.2 lesson, and remember, you don't have a secant button. So if the secant of pi over 7 is going to be the same as 1 over the cosine of pi over 7, and that's what you would type in your calculator. On A. Did you type 2 pi over 5 as an actual fraction? Then it's probably dividing the pi with the 5. Oh, you have to type pi. Sorry. You do have to enter the pi. So you are typing exactly what you see. The only time you don't type pi in the calculator is when you're doing like conversions where the pi is going to be canceled, or when you're reducing fractions. So here, did you get 1.1099? Okay, any questions on how to use the unit circle to find those values, or how to just type this in? Because now we're getting to the graphs. The graphs are tying it all together. They're giving you a visual of, it's more so for the ones on the unit circle, not these random ones that give you ugly decimals. But the graphs are showing you the relationship between the values as it goes around the unit circle. There's a pattern to it. I have good news. I used to make my pre-cal class graph these by hand. There was a 2-part to the test because at the time, this was when the college just gave us free range. So I made part 1 where they had to graph one of each by hand, and then part 2 was where we used the graphing calculator. The good news is now, because of my math lab, I can see that my math lab is going to have you use a widget to graph it, which means you basically just have to be able to do the anchor points and then understand the transformation, and you type it in, like if it's either shifting right, shifting up, you type that in, and then it graphs it for you. You don't have to generate the entire T-chart that I used to make my pre-cal students do. So you're welcome. Okay, so look at this slide right here. We're looking at the graphs of sine and cosine first because they're very similar. Tangent's a totally different ballgame, and that's because tangent is taking the coordinates and dividing them, right? Sine and cosine is just x or y. Remember? So that's why tangent's totally different. Looking at this picture right here, this was just a little bit of the unit circle to kind of remind you, where these numbers are. Start getting comfortable with where they land. Look at the unit circle so that you are comfortable and you kind of have an idea of where the radians are. Remember, if I was to ask you to fill in the unit circle, then you need to memorize quadrant 1 and use it to fill in the others. If you'll just get quadrant 1 down, you can use it to fill in the remaining quadrants. You just have to remember your signs. Alright, so we're going to let x be the angle measurement, and now we're going to make t-tables or t-charts of what the sine and cosine graphs would result in. And I think we go to tangent. Yeah, then we're going to go to tangent. Okay? So because we are graphing in radians, your x and y axis now is a little different than what you're used to. If you look right here, the y-axis looks the same in terms of just plain numbers, but look at your x-axis. Remember we said on the last slide that we're going to let x be the angle measurement, so that the degree of rotation, or radian of rotation. So for instance, anything right here, don't write that. Anything that falls right here is the result of rotating one complete time around, right? 2 pi. Anything that falls right here would be the result of rotating only half, the 1 pi. Does that make sense? Look at the T-chart to the left. Instead of x, comma, y, now we have theta, comma, sine of theta. Because we're going to evaluate the sine graph to see what we get. When you look at this, you probably are thinking to yourself, I have no clue how this is fixing to pan out. You need your unit circle. Pull your complete unit circle paper out, put it side by side, and watch how we fill this in. Sine means look at what? Sine means look at the y on the unit circle. Okay, find 0 pi. What's the y? Find 0 pi on your unit circle. And what is the y coordinate there? 0. Find pi over 6. What's the y coordinate? 1/2. Let's go with decimals, y'all. Just so that we can graph it easier. Find pi over 4. What's the y coordinate? And if you went to your calculator and you typed square root 2 divided by 2 and went to the nearest tenth, this is what you get. Find pi over 3. What's the y coordinate? And as a decimal, that's about 0.9. Pi over 2, the y coordinate's 1. And then now these exact numbers are fixing to repeat, but might have a different, or might have a negative in front of them, right? Now we're at, what is it, 3 pi over 4. What's the y coordinate? All right, so that's 0.7. At pi, so visualize it, that's the 180. What's the y coordinate? 0. 5 pi over 4 is going to be negative square root 2 over 2. 3 pi over 2 is the due south one, so the y coordinate is negative 1. 7 pi over 4 is negative square root 2 over 2. And a full rotation, 2 pi, what's the y coordinate? 0. All right, we're going to plot this on the graph. 0.5 should be right in the middle. 0.7 should be a little past it. 0.9 should be almost to the whole number, right? Okay, so you've got 0, 0 right here. Then if you go pi over 6, you end at half. You will notice pi over 6 is not on our x-axis, right? Pi over 6 is not on, I should say x slash theta. Pi over 6 is not on the x-axis, so let's just skip to the next one. Pi over 4 is 0.7. So 0.7 means just a little above halfway. Pi over 3 is not on the x-axis. Pi over 2 is, and it's 1. 3 pi over 4 is 0.7. Pi is 0. 5 pi over 4 is negative 0.7. You have to be careful here because this gap where the numbers are is the 0.7. It's not below it. 3 pi over 2 is negative 1. 7 pi over 4 is on here. And then 2 pi is 0. We've only graphed a snippet of it. This keeps going. But that is the, I call it the anchor chart. Or the mother function, if you want to call it. It's the original complete full cycle of going all the way around the unit circle one time, this is where it lands. This gets repeated over here with a nice smooth rhythm. So like if this is going this way, then it's gonna go like that, right? You see? So we're gonna fill it in. There's a pattern to it. Come on, back up. All right. So this is going to go to about 0.7, and it's going to go to -1. You see the pattern? Every other one is 0.7. Every other one is a 0.7 marker, getting you closer to either 0 or 1 or -1. And then now I'm going to just draw a smooth curve through it with arrows because this does keep going. Then I want you to take a highlighter or a colored pen or take your pencil and make these points that I'm fixing to show you either bigger or make them squares, I don't know, or make them stars. I'm not going to make you do this by hand. I already told y'all I'm not doing that. But I want you to understand there are there's 5 key points that will always help you know that this is sine. The 5 key points, I say 5. Oh yeah, that's why. I was like, why is there 5? There's only 4 quadrants. The 5 key points come from, on the unit circle, asking yourself, what's the y value here? What's the y value here? Y value here, y value here, and then full rotation back, y value here. That's the 5th one. Okay? You should know those points. This is 1, 0. This is 0, 1. This is -1, 0. This is 0, -1, right? And it's just, what's the y? So you have to think to yourself, so it's the poison that's going on. I didn't hear it. Oh, we've got buyers. Y'all want cookies? They're getting their money. Yeah, absolutely. There's sugar cookies. There's fun. Bailey's like, I didn't get
It's $2 to use the 50 cents that you get back.
I need try. Well, I think it's fixing to cut off. No, don't. No, absolutely not. Those cookies are so rich, like. Well, then you're still. Then you have to brief cookie interruption. Okay, so here, let me get my highlighter and show you what I mean. This is just going to help you remember which function, which graph is which. Sine and cosine graphs look very similar. In fact, they are identical with one main difference, and that is where it starts right here. Okay, so I call that my like anchor point because I know that the sine of 0 means I have not rotated at all, which means the coordinate point is 1, 0. Sine means what's the y value, so it's 0. So that's an anchor point. Pi over 2 is the due north at 90. What's the y value? 1. Pi is 180. What's the y value? It's 0. 3 pi over, didn't mean to highlight the axis. 3 pi over 2 is due south. What's the y value? It's -1. And then as you complete the rotation, 2 pi puts you right back at 0. So what's the y value at 0? If you can just, it's not memorized because you're just answering the question looking at your unit circle, but if you can kind of wrap your mind around that, it makes this so much easier. Let me erase this. Now we're going to fill in the cosine graph. And the cosine graph means we're looking at the what? The x coordinate this time. You're repeating the exact thing that we just did, but now we're pulling the x value. You will notice we have the same type of answers. It's 1, 0.9, 0.7, 0.5, or 0, or negatives. All right, so at 0, the x coordinate's 1. At pi over 6, it's going to be 0.9. Pi over 4 is 0.7. Pi over 3 is a half. Due north is 0. I'm just going to fill it in. Y'all can just go up here if you need to. Whole chart print for you because mine did not. Good. Okay. Mine didn't print. I had to fill mine in. All right. Now we're going to graph it. So 0, 1. Pi over 6 is not an option, okay? This is hitting all of the 45 and quadrantal angles. It doesn't hit the 30 and 60 angle marks. That's why I just wanted you to understand what it is as a decimal, but that's why it's not on the graph. All right, pi over 4 is about 0.7. Pi over 2 is 0. 3 pi over 4 pi. You can see the pattern. So that is the full, complete curve cycle before it starts to repeat the pattern, okay? To get the rest, you would just keep this pattern going in this direction. Just remember you're hitting a 0.7 marker every other one. So right here, 0.7, 0, negative 0.7, negative 1. Then I'm going to draw my curve because I miss one of those. All right, don't turn the page though. Hold on, I've got something else to add to it. I'm going to take my highlighter and highlight the anchor points. That would be the quadrantal ones. So like 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now I'm going to ask you, or I'm going to tell you, so the top is sine, the bottom is cosine, right? They look identical. It just looks like one has just been shifted over and it starts in a different spot. How are you going to memorize that sine is this top one and cosine is the bottom one? When you get to the math lab homework, there's a widget and there's a button for the sine graph, there's a button for the cosine graph, and they don't label it. There's one key difference. This is how, I mean, everybody has their own ways. I have this stupid way. It all revolves around this one. The sine graph starts at 0, 0. The cosine graph starts at 0, 1. Here's how I remember it. I think cosines like the word coaster, a roller coaster. This looks like a roller coaster. And I always think, what's the best part of a roller coaster? That's when you're already up there and you're fixing to drop, right? So that's how I memorized that the cosine graph starts up at 0, 1, because the best part of a coaster, for me, if you're Riles, you can't stand that part. He hates that part. But so that's how I memorized, okay, cosine's the one that starts up high, and then sine's the one that doesn't.
They could do it with the S and the C. The S is draw one, the next two zeros, the C is draw one.
Love it. See? I almost felt like, sorry. So you're saying like you could, well, I don't want to think of an 8, but you're saying like you could make it into 2 zeros. Love it. And then like 0, 1. Love it. That's the way that I actually, well, I showed y'all I teach complementary and supplementary. I learned that from a kid. Learned this from you. Love it. Let's see. Domain and range, you're not out of the woods with that. I know y'all hate domain and range. Domain means, can you give me an idea of what x values are covered? What is the graph doing? It's going and going and going. So the domain would be negative infinity to infinity. How's it going? Remember, you don't put brackets on domain because that would mean it's touching infinity, and that's impossible. Infinity is a direction, it's not a number. And then range. Range means turn your head sideways and tell me what y values is it oscillating between. So the smallest y value produced is, when we say y value, we're talking about like, not necessarily y value, but the vertical axis. So what's the smallest value coming out of both of them? -1. What's the largest value coming out of both of them? +1. And it is hitting those. So it's running from -1 to +1 with brackets. Would you say cosine has the same exact domain and range? You would be correct. So, depending on how you wrote this on your paper, you could say that this is domain and range for both. Or you could just write it again on the cosine graph. Alright, now we're going to look at tangent, which is my least favorite because it's just weird. Tangent's weird. Tangent makes me uncomfortable. Alright, tangent requires you to divide y over x. So there's some of these up here that we're not going to divide because it's an ugly decimal. We're going to hit the anchor points so then we can kind of get an idea of what the graph is. So think about it. Think of your quadrantal angles, right? So you've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Think of those numbers. If we're doing y over x, right? We're doing y over x. At 0 on the unit circle, what would I be dividing? 0 over 1, which is 0. We are going to skip pi over 6. Let's hit the 45-degree markers because those are really easy numbers. If I divided y over x at pi over 4, I'm going to be dividing the exact same number. Where did I lose you? Did I lose you? Okay. If I divide at pi over 4, right here. Oh. Right here, right? I'm dividing these numbers. Don't actually divide them. They're the same exact numbers, right? Pi over 2 divided by pi over 2 is going to be 1, which is why we wanted to hit that one because it's nice and easy. It's going to crash. Piece of crap. That means all my writing's over. All right, keep going. So pi over 4 is 1. slash through pi over 3. Pi over 2, that's due north. Tell me what the fraction would be. It would be undefined. You'd end up with 1 over 0, right? Okay, we're right here. We're just going to write undefined. Alright, 3 pi over 4 is one of the nice ones where the x and the y are the same number. It's just going to be a negative 1 this time. Pi is the 180 mark. The fraction would be 0 over 1, which is 0.
Why are we slashing for time?
You can find them, but if we find the others that are nice and convenient, we can do it in our head, we're still going to get the same graph. So I'm just slashing it for time. Like, it's not necessary to know where this lands because you're fixing to see the graph, and it's going to connect, it's going to cover it. You know what I mean? We're graphing the pretty ones. I guess I should have said. 5 pi over 4, you should get 1. 3 pi over 2, that's the due south. You should get a problem. 7 pi over 4 is going to be negative 1. And then 2 pi is a full rotation. Now, do you remember the vocab word to describe when something is undefined? What's on the graph if it has an undefined value? A hole or an asymptote. There it is. Tangent has asymptotes, and it's the mother function for the tangent graph is always at, if you think about it, the y-axis, the due north and the due south values, because that's where, when you're setting up y over x, you end up with 0 in the bottom, which is a problem. All right, so we're going to plot our asymptotes first. We're going to put dotted line at pi over 2 and 3 pi over 2. Now, if that's our asymptotes right there for the first full cycle, we can reflect that over here. So we're going to put another asymptote at negative pi over 2 and negative 3 pi over 2. And then now we're going to plot. All right, so we have a point at 0, 0, pi over 4, 1, 3 pi over 4, negative 1, pi is 0, 5 pi over 4 is 1, 7 pi over 4 is negative 1, 2 pi is 0. Looks weird. That's because we're kind of splitting right here. There was a, where do you think the point should be for negative pi over 4? Look at the pattern. Where should the point be for negative pi over 4? Negative 1. And then you're going to copy those 3 in the next section. So you got negative, 0, 1. Copy the next 3. You only have space for 2 of them. Here's the curve. Try your best to make it curve. You don't want to be like, it doesn't do that. It's a curve. Now you can see why tangent drives me nuts. I like sine and cosine because it's one graph. I don't have all these little sections. All right, I want to take I want to make 3 notes about tangent, the pattern, okay? The three notes refer to where is tangent undefined? Where is tangent always 0? Where is tangent always like 1 or negative 1? So wherever you have space, let's make a note. Where is tan undefined? Well, the only way to get undefined is to take a number and do what with it? Divide it by 0. So you have to think to yourself, if I'm taking a number and I'm dividing by 0, that would mean what value has to be 0 according to the tangent formula? The x. So the only way to get undefined is to divide by 0. Well, in tangent, that would mean x. I'm going to draw an arrow suggesting which means where x is equal to 0. Now you have to think to yourself, where is x equal to 0? Right? I didn't mean to do that. I meant to do the unit circle. Where is it? Where is x equal to 0? This. That's what I meant to circle. That's where x is 0, right? On the y-axis. So it's hitting every pi over 2. And then this is another pi over 2. What's the gap? What's the radian rotation gap from here to here? So, yes, thank you. What's the gap from here to here? Pi, right? It's half the circle. Just the gap. I'm saying, like, what plus pi over 2 would give me 3 pi over 2? It's pi. So the way we're fixing to write this is a very intuitive way to cover every single time tangent would be undefined. It's going to come from pi over 2 plus or minus any multiple of pi. It's going to hit on the y-axis. So watch how I write this. So we said that it's this formula, which means x is 0. Where is x 0? X is 0 at pi over 2. And then I'm going to write plus or minus to show you can go either direction. And we're hitting any value of pi, right? So plus or minus pi. Now there's multiples of pi. You technically could put an n there and say where n is any integer. You could subtract 4 pi, 2 pi, 3 pi, doesn't matter. But that's just an intuitive little way to say, here's where tangent's undefined. Where's tangent 1? Well, the only way to divide two numbers and get 1 is if the numbers are the same, right? What part of the unit circle has the same x and y values? The 45 degree markers, right? Pi over 4. So basically, where's tangent 1? Any 45 or pi over 4 radian. There's a pattern with all the sine, cosine, tangent functions. The good news is you don't have to graph this by hand. I'm just trying to stress to you what the pattern is so that you're comfortable with it. When you are graphing it in the widget, you understand it. Look at the next slide. Not a lot to write here. We already did this. This is just putting it in nice print what the domain and range is. Go to this slide. Couple of new vocab words here. They're really not that bad. You're just going to have to practice them. There's a new vocab word in terms of the period of the trig function, and then in terms of the amplitude. Now, amplitude's really easy to remember because I think of amps in terms of music. Like if you turn the volume louder, you just went, you're like higher amps, right? You know what I mean? Go with me, sound waves. So that's the way I think of, like, if the amplitude is a bigger number, the curve is more dramatic, like the sound's going up. If the amplitude is a small number, it means you're turning it down. It's not as, another way to think of it is like earthquake, the Richter scale, right? Let's take some notes on here. What does the periodic portion mean? It's referring to like a pattern. I do want to adjust this where there's S. S is referring to that, like right here, the rotation. I want to change that to theta because I don't want you to confuse that S with the arc length from that one formula. So everywhere there's an S, you're going to put a theta so that you'll remember we're talking about rotation. If I ask you for the amplitude, it's not the space between the highest curve and the lowest curve. It's actually just half that. So it's the space from either the highest or the lowest. Doesn't matter because they're symmetrical, right? That's why there's a one over there too. And it's just like how far from, if you want to think of it as like volumes off, how far from the x-axis does the curve stretch to? How far away from the x-axis is the curve, which is the gap right here. So this is the sine function, the mother function. What's the amplitude of the mother function for sine? It's 1, because the curve is only going up 1 unit from the x-axis, or it's only going down 1 unit from the x-axis. What's the period? The period means tell me from what to what do I get one complete pattern that then copies all across the graph. And that would be from here to here is the curve before the pattern repeats. Because when you hit over here and keep going, now you're repeating this back here. You see that? So what is the period? That means tell me from what radian gap do you get one full cycle, and it would be 2 pi. Because that's one full rotation. Okay? Cosine's the same way. Now tangent's a little different, and that's because of those deadgum asymptotes. Go to the next slide. The next slide is letting you know when you have a negative rotation, sign of a negative rotation means that your y value is going to be negative. If it landed like here. Hey, by the way, hold on, I can tell you exactly this here. The sine function is odd, the cosine function is even. We need to take some notes right here. This is coming back from college algebra, so I know y'all slept since then. When we say that the sine function is odd and cosine is even, here's what we mean by it. Odd means it's symmetrical. By a 180-degree rotation. Odd is symmetrical by a 180-degree rotation around the origin, by the way. And if you think back to college algebra, that's how I told y'all to memorize. Odd means the origin. You're taking it and you're turning it upside down, and it's the same graph. What time does the tiger walk start? Do you want to leave that here and come get it? Like your stuff? Okay, I didn't know if you parked it here. You can leave that on my desk if
You don't want
feel
to carry that
it.
walking, Gracie. You don't want to walk carrying it. Yeah, that's true.
Sure.
That's what I was trying to think.
I'll leave it here.
Put it on my desk though, because my next class is full.
Okay.
Um, Odd means symmetrical around the origin. It would be the equivalent of taking your paper and turning it upside down, and it's the same graph. Even if you think back to college algebra, we went with the quadratic mother function. It sits right in the middle of the y-axis, and you can fold it on the y-axis, and it's the same graph. So this would mean symmetrical across y-axis. There's no symmetry over the x-axis because then it, well, in this case it'd still be a function, but back in the college algebra class we learned that sometimes it's not a function.
So is the sine function always odd and cosine's always even?
Yeah. Doesn't matter, and that's because there's a pattern. It's because of that rotation. If you think about it, like you're hitting those values on a full rotation, and then it's just repeating every time, and that comes back to those reference angles. You get the same answer. Doesn't matter how many times you rotate it. Yeah. This right here is a very helpful slide that gives you all the properties of the mother functions for sine and cosine. Okay? It tells you that, hey, they're continuous, which means you don't have to pick your pencil up. That means tangent is discontinuous. Very good, not continuous. The period is saying, I would take your highlighter and I would highlight that, we'll call it the mother curve. I don't want to say the mother function because it's not the whole function. We'll call it the mother curve. Highlight that initial mother curve for sine and cosine. They are different in terms of where they start. Remember a roller coaster, best part is up at the top, or the making it into 0, 0 and 0, 1. Domain is all real numbers for both. Range is oscillating between -1 and 1. The amplitude on the mother functions is just 1. This part right here, this odd and even part, is saying if you were to evaluate sine of some negative rotation, you will get the same thing as if you just negate, meaning make negative, the sine of that positive rotation. If you were to evaluate the cosine of a negative rotation, you will get the same thing as the cosine of the positive rotation. Those are shortcuts, and it's because of their symmetry. The next slide is what you saw us doing already. We were writing it on the slide with the tangent graph. So here it is written out nice and neat. Where is tangent function undefined? We said that it is any theta value that hits due north, right? So pi over 2, but we're going to account for any possibility, which would mean that it could be positive pi over 2, or it could be negative pi over 2. Then it's going to hit 3 pi over 2, or if you were going negative 3 pi over 2, and so on. Where's tangent equal to? Alright, let's wrap this up so we can, do y'all want to go to the tiger walk? Okay, we'll wrap it up so anyone that wants to go can. Where is tangent function equal to 0, 1, -1? Okay, so tangent of the value is 0 when you have to think about it, so that means you're dividing 0 over a number. So 0 over any number, tangent's y over x, so that means that this has to be the the y value, right? The y value is 0. Y value 0 means what? You're sitting on the x-axis. You're at 0, pi, or 2 pi. And then your rotation is just every 1. So the first one is 0 pi. I don't think I wrote 0 pi. I did actually. I wrote 0 pi. Okay. So tangent is 0 when the y value is 0. So the answer is 0 pi, if you want to write that there, or just 0. And then pi, positive or negative pi, then positive or negative 2 pi, and so on. All right, wrapping it up, go to the next slide. This is just letting you see, you know, like when you're got the domain and the range, this is where tangent is not as convenient as sine and cosine because you do have these asymptotes here. So tangent is undefined here on these asymptotes. Tangent is 1, 0, negative 1 on these points. This is just separating those values and showing you where that's happening. They're not superimposed on the same graph, okay? And that all comes from, because tangent's y over x. This is the reciprocal functions, which we are not graphing. Hallelujah. But I wanted to show it to you. This is cosecant, secant, cotangent. You'll notice cosecant and secant look totally different. And that's because, remember, that comes from 1 over x, or 1 over y. That's why now all of a sudden you have asymptotes. Because sometimes 0 is going to be in the bottom. And this sums it up. And in sync. Done. If you're wanting to do the tiger walk, go on down there.
I just read it.
Yeah.